in the course of the quantum annealing. It releases the qualitative speed up. So this is the main message of this presentation. So we also consider the non-ideal case, the case where the control of the transverse field deviates from the ideal situation. I explained this meaning of this sentence later, but for non-ideal case, we can expect quantitative speed up, at least. For this topic, we had a poster presentation given by the Yu Yamashiro. He is the collaborator, one of the collaborators of this work. So if you have interest in about this topic, please check his poster. So we set the target Hamiltonian now. In this presentation, we consider the p-spin model as a target Hamiltonian. It's a simple form, this one. When we set this p-spin model as a target Hamiltonian, we have the system has a first order phase transition in course of the quantum annealing. Although the ground state is so trivial, but it is difficult for the quantum annealing to solve. So we want to consider how to avoid the way to avoid the first order phase transition. The one of the method, using the non-stochastic term, it is shown in this paper. They show that by using the non-stochastic term, the first order phase transition is changed to the second order phase transition. But in this presentation, we showed that by using the individual control of the transverse field, we can erase the first order phase transition for this p-spin model. So for p-spin model, we set appropriate the gamma I. Now we set the gamma I like this. So with this style of the gamma I and this driver Hamiltonian, we can rewrite the driver Hamiltonian like this. This is for the large system size. So important point is tau. The parameter tau controls the number of spins interacting with the transverse field. We can control the tau from 0 to 1. And finally, when we set the tau equal 1, we completely switch off the transverse field. For this Hamiltonian, we can calculate the free energy and the self-consistent equation of the water parameter like this. From this equation, we can estimate the phase transition in the course of the quantum annealing. Then this is the phase diagram. Now we have the two control parameters, S and the tau, this axis and this axis. And this is the start point. Here we only have the transverse field. And this is the end point of the quantum annealing. Here we only have the target Hamiltonian. These lines indicate the first order phase transition for the p equals 3, 4, 5. We can analytically calculate the edge of this line. It is critical point like this. In this point, the system has the second order phase transition. So this arrow shows that when we set the tau equals 0, this path, which is corresponds to the conventional quantum annealing. I mean, when we set the tau equals 0, the transverse field is homogeneously applied to the spins. So it is a similar situation to the conventional quantum annealing. As you can see, this path crossing the first order phase transition line here. And you can see the first order phase transition appears at this point by evaluating the order parameter. This is for the p equals 3 and the tau equals 0, this point. And we have the order parameter discontinuously changed at this point. It is a typical behavior of the first order phase transition. And then when we control the tau from 0 to 1, here we set the tau equal S. This path avoiding the phase transition line for the P equals 3, like this. By calculating the order parameter, this plot shows the order parameter for this path. There is no discontinuous change. There is no typical behavior of the first order phase transition. So that at least by taking this path, we can avoid the first order phase transition, which leads the qualitative speed up. We can expect the qualitative speed up by controlling the tau by using this inhomogeneous transverse field. So we can check the phase diagram by evaluating the entanglement entropy. To calculate the entropy, we divided the system into two half subsystems, and we calculate the entropy between them. And this 3 plot is a result for these 3 passes. For the path A, it is for the conventional style of the quantum annealing. And this is the entanglement entropy for the path A. At this point, the entanglement entropy discontinuously changed. It is a typical behavior of the first order phase transition. For the path B, which is going through the critical point, this one. For the second order phase transition, generally the entanglement entropy continuously changed. This plot shows the result. So this is the typical behavior of the second order phase transition. So for the path C, which avoid the first order phase transition line, this. So this is not, this is different from the typical behavior of the first order phase transition. So that this is evidence that by taking path C, which avoids the phase transition line, it actually avoids the first order phase transition. So we also calculate the energy gap for the finite system size N for this path. To calculate the energy gap, we diagonalize Hamiltonian, and to diagonalize Hamiltonian, we for the calculation convenience, the n1 minus tau on the sigma should be the integer, so that we round up the n1 minus tau for the calculation convenience. This step form is come from the rounded up the n1 minus tau. It is show the for the n equal 5, 10, 100 energy gap. So when we switch over the transverse field at first sight, the energy gap takes the minimal value here. And in the right plot, in right graph, we plot the minimal energy gap as a function of n in the log plot. And the blue dot shows at this point. And the yellow dot is the minimal energy gap when we use the conventional quantum annealing. So as you can see, when we use the conventional style of quantum annealing, the minimal energy gap exponentially decays. But if you use the quantum annealing with individually controlled transverse field, the minimal energy gap decays in the polynomial. So according to the Adiabatic theorem, the annealing time is proportional to the inverse square of the minimal energy gap. We can evaluate the annealing time by the Adiabatic theorem. So this graph shows the individual controlled quantum annealing is better than the conventional style of the quantum annealing in sense of the annealing time. So next. We also consider that when the target Hamiltonian has not only p-spin Hamiltonian, but also the random longitudinal field. For this model, the non-stochastic Hamiltonian method doesn't work, which means the non-stochastic Hamiltonian does not remove the first-order phase transition for this model. But with the individual control of the transverse field, by controlling tau, we can take the path, avoiding the first-order phase transition, here to here. This graph is the case for the HI takes the plus or minus H0, and then we set H0 equal 1. We can also plot the similar graph for the Gaussian distribution when HI follows the Gaussian distribution. So, as I show you that by using the individual control transverse field, we can accelerate the quantum annealing. But these results, we assume that the zero temperature case, and we completely control the transverse field. So from now, we consider the non-ideal case. For example, the finite temperature case, where the transverse field deviate, the controlling the transverse field deviate from the ideal case. The case of the finite temperature we discussed in the poster. So now we show the second line, the case of the second line. So when, this is show the non-ideal case, this is for the, when we cannot enough switch off the transverse field. I mean, the weak transverse field remains here, the factor gamma. For this model, for this the transverse field, in the phase diagram, the another first order phase transition line appears here. This is for the p equals 3, then gamma equals 0.01. This is the original one. So this line, we cannot avoid. We cannot take the bus. This line is an inevitable lines, so we cannot expect the qualitatively speed up for these cases. But we can show that another first order phase transition line is weaker than the original one, which is shown by the calculated width of the free energy barrier. So at first order phase transition point, the order parameter has a discontinuously changes here. So we calculated this width of jump, the delta m, which is equal to the width of the free energy barrier here. So if the delta m is small, it is preferable for the quantum annealing in sense of the quantum tunneling. Now we calculate the width of the free energy barrier for this gamma. The result is this one. When we take the path going through the blue square, it is for the conventional quantum annealing. The width of the free energy barrier is 0.8. And if we take the path going through the red circle, it's crossing the new phase transition line like this by controlling the tau, parameter tau. At this point, the width of the free energy barrier, the value of the width of the free energy barrier is 0.1 or 0.2 something. So this shows that another first order phase transition is weaker than the original one. So we can expect the quantitative speed up for this model. We also consider another non-ideal case. The difference from the previous gamma is finally this gamma I take 0 at end point here. But in this case also has another phase transition line, inevitable phase transition line here. But width of the free energy barrier is also same. So if you can take the path crossing the new phase transition line is better than the original path going through the original phase transition line. So this slide for the summary. Here we show the individual contour of the transverse field. We can avoid first order phase transition, which is problematic for the quantum annealing. For the ID case, we can expect a qualitative speed up. Even if the non-ID case, we can expect the quantitative speed up. So we have the poster presentation for more detailed discussion. In this poster, we discussed that for the finite temperatures and the analysis by SBMC, the case of smooth stitching of the transfer field. So yeah, please check this poster for detailed discussion. Thank you for your attention.
Thanks a lot, Yuki. We have time for some questions.
So in the last part, if you have the p-spin model plus the random local fields, how do I have to choose the gammas? Do I just choose them randomly, or is there a recipe how I calculate them?
Which slide do you?
Yeah, this one, yes.
Yeah.
Now the gamma I.
Same gamma I use. I mean.
So they are.
Idea. Yeah, this one.
So they are independent of the randomness of the local.
Yeah.
Mm-hmm. Okay.
Could the next speaker please come set up? Thanks.
Hi. So I have just in this non-ideal case that you were discussing.
Wait. This is?
Yes.
Yeah.
Okay, so this first order phase transition, is that a consequence of a mean field analysis that you still get this another first order phase transition? Does this come from the mean field analysis?
Yeah.
Okay, so maybe if you do a fully quantum analysis, there's still a gap in a way around this first order phase transition, because in the p equals 3 model, if you have a non-stochastic driver, you can also get around the first order phase transition if you use a fully quantum analysis of what's happening in that phase transition. It's just classically that the Landau result is that
it's a classical.
Right, so if you did a fully quantum treatment here, maybe you would see a way around this first order phase transition. Maybe it softens into a second order.
I'm sorry, I'm never considered that. Yeah.
Oh, and the other thing was that the beta, you're scaling, what was the value of beta? You said you went from in the ideal case, you went to...
This is the beta, this is a zero temperature case.
Yeah, no, but you presented the scaling going from exponential to polynomial. You had n to the beta. What was the beta?
Beta?
In the ideal case, yes. Like, does the scaling become quadratic, or?
Close to quadratic.
Close to quadratic, okay.